So we take again the tau plane, and again we take these two lines. So let me draw them a little big. So now I am also considering the part of the region that is the reflection about the imaginary axis of the region omega. Okay, so this is real part of tau is equal to 1, this is real part of tau is equal to 0, and this is real part of tau equal to -1. Okay, and so this is 0, this is 1, this is -1, alright, and I draw this semicircle centered at half, radius half. Okay, and then I have omega here. Okay, and let us call the reflection of omega as omega prime. Okay, in fact in the very same methods that prove that we will show to prove that lambda maps omega holomorphically isomorphically onto the upper half plane, will show that it will map omega prime holomorphically isomorphically onto the lower half plane. Okay, so it is certainly not out of place to consider omega prime. Okay, and so you see I have my situation like this. Now what I am going to do is I am going to take a line segment, I am going to take a line segment here, or rather let me take a line here parallel to the real axis. Okay, and with imaginary part of tau is equal to say some y naught. Okay, so this length is y naught, right, and let me give names for these points. So this is O, this is A, right, and then B, C, D, this is E, I guess. Yeah, so you see this is O, A, B, C, D and E, right, and I am going to look at first of all I am going to for reasons that will be clear, because I want to make use of the the functional equations. Okay, I am going to first study the effect of the transformations tau going to -1 by tau and tau going to -1 by tau plus 1 on parts of this diagram. So what I am going to do is I will draw another piece of this of the same diagram, another copy of it rather. So you see so here I am again in the tau plane, right, and maybe I will call this a tau prime plane, right, and again let me draw this so you see so this is again 1, this is 0, and then I just want to show this circle, I just want to show these two circles here, so I am going to draw them as dotted lines, because these circles, these semicircles are in the source plane. Okay, and well, let me draw these dotted lines like this. Okay, and well I am going to do the following thing. I am going to look at the first I want to look at what is the image of this line, okay, under two transformations, okay, which is tau going to -1 by tau and tau going to -1 by tau plus 1, alright. So this will involve a little bit of computation. So the first thing I want to say is, well So you see consider the image of this line imaginary part of tau is equal to y naught, okay. This line which is parallel to the real axis, consider the image of that, okay, under let us say tau going to -1 by tau, okay. So which means, so that is my transformation is tau prime is tau prime is equal to minus 1 by tau. This is my transformation, okay. You see tau going to -1 by tau is actually you see it's a Mobius transformation, and you know Mobius transformation maps straight lines and circles onto straight lines and circles. Now you can see that, you see if I put what is the image of B, okay. So B is the point, if I calculate tau prime, so tau prime of tau is -1 by tau. So if I calculate tau prime of the point B, it will be just tau prime of, well, the point B is 1 plus, it is 1 plus I times y naught, this is what it is, and tau prime of tau is supposed to be -1 by tau, so this is going to be -1 by 1 plus I y naught, okay. And so this is going to give you, if I multiply by the conjugate, I will get 1 minus I y naught by 1 plus y naught squared. So I am going to get the point -1 plus I y naught by 1 plus y naught squared, okay. This is what I am going to get, and this is and where will this point lie? So you see so this point, notice, so B has to go to this point, alright, here, okay, and well, if I calculate, also notice that this line, okay, this whole line is mapped by tau going to -1 by tau onto this circle, onto the semicircle. Yeah, so the claim is the following, the claim is that, you see, the image of this line, alright, under this map is going to be a circle here, and let me draw it with the correct orientation, then I can explain to you B to C, yeah. So it's going to be a circle like this. This is what I'm going to get, okay. And in fact, you see B, C, D will go to these 3 points. So this is the image of, so this will be B prime, this will be C prime, and this will be D prime. This is what you will get, okay. This is what you get. So B prime will be tau prime of B, so it's this point, it's a point with a negative real coordinate -1 by 1 plus y naught squared, and if you calculate what is C prime will be tau prime of C, it's going to be tau prime of, what is C? C is just I y naught, so it's going to be tau prime of I y naught, but tau prime of tau is supposed to be -1 by tau, alright, so I'll get -1 by I y naught, and so I'm going to get I by y naught, alright. So what I'll get is, I'll get this point, so the C prime will be this point on the imaginary axis, I by y naught, okay. So, and what will D prime be? D prime is the image of D, so it's, and what is D? D is -1 plus I y naught, so I'll get -1 plus I y naught, if I plug it in here I'll get -1 by -1 plus I y naught, and that's going to, if I multiply and divide by the conjugate, I'm going to get minus of -1 minus I y naught by 1 plus y naught squared. So I'm going to get 1 plus I y naught by 1 plus y naught square. Okay, so so that is this point D. Okay, and you can see that you see the if you look at, see, first of all B, C and D are being mapped to these 3 points. Okay, C is on the imaginary axis and B and D have the same y coordinate. You see B, the y coordinate of I mean B prime and D prime have the same y coordinate. The y coordinate of B prime is y naught by 1 plus y naught square. The y coordinate of D prime is also y naught by 1 plus y naught square. So they are at the same height, and then you know if I let tau to tend to infinity, okay, tau, now you see my tau is varying on this line. If I let tau to tend to infinity, alright, then essentially that means you know every point on this line the imaginary part is fixed to be y naught, so I will have to let x to tend to infinity. Okay, but if I let tau to tend to infinity, minus 1 by tau will go to 0. Therefore the point at infinity on this line, okay, is going to be mapped to 0. So therefore what you will get is the image of this whole line will be this circle. Okay, and by symmetry you can see that this circle has to be tangent to the real axis, okay, because of conformality. Alright, so this is what you will get. So so the important thing that I need is, you see that as you go from B to C, okay, the image in the tau prime plane will trace B prime to C prime, and as you go from C to D, the image in the tau prime plane will trace C prime to D prime. Alright, this is what will happen. Now then I also want to look at what is going to happen if I take the tau double prime. So let me, so this is the effect of looking at this line, the image of this line under tau going to minus 1 by tau. Let me look at the effect of that line under tau going to minus 1 by tau plus 1, okay, which means I just have to translate this by 1. Alright, so what I will do is consider the image of imaginary part of tau is equal to y naught under tau going to minus 1 by tau plus 1. Okay, so that is you know tau prime of tau is so let me call it as tau double prime if you want. So tau double prime of tau is minus 1 by tau plus 1. Alright, now you will see that if I draw the diagram in the tau double prime plane, okay, so what will I get? I will get, you know what to expect. So this is 1, this is 0, and well, this does not look the same length as this doesn't look the same length as this is. So let me draw it. Right, so this is minus 1, right, and then again you have this semicircle centered at half, okay, and what will be the image of B, C, D under the mapping tau going to tau double prime, which is minus 1 by tau plus 1, okay, it will be just translate of this circle by 1. Alright, and I will get again the corresponding points B double prime, C double prime and D double prime. So what I will get here is, well, you can imagine a mirror image of this circle here, okay, and then I will again get a circle here being traced in this manner, and I will get that this is, well, this point here will be B double prime, this point, so yeah, because it is just translation, so this will be C double prime, and so this will be C double prime, and well, and this point here will be D double prime. okay. So the point I want you to understand is that if you go from B to C in the tau prime plane, I will get this portion of the arc from B prime to C prime. If you go from C to D, I will get this portion of the arc from C prime to D prime. If you go from B to C in the tau double prime plane, I will get this portion of the arc from B prime to C, B double prime to C double prime. And if I go from C to D, then in the tau double prime I get this portion of the arc from C double prime to D double prime, alright. So I will use this now, alright. I will use that in conjunction with this estimate, right. So now consider the image of, let us consider one by one, let us consider the image of BC, okay, under lambda of tau, okay. Now consider the image of BC under lambda of tau. BC is parameterized by x plus I y naught with x varying from so when I am at B, x is 1, when I am at C, x is 0. So x is decreasing from 1 to 0, okay. This is the orientation, x is starting at 1 and it is going to 0 if I move from B to C. Tau double prime of tau is what? It is tau double prime of tau is minus 1 by tau plus 1, okay. First let us look at lambda of tau double prime with tau double prime on B double prime C double prime, okay. So let us look at what is the image under lambda of this piece B double prime C double prime, right. So you see what you will get is, you know, lambda of tau double prime, but you know tau double prime is minus 1 by tau plus 1, so it will be lambda of minus 1 by tau plus 1, okay. And you have a functional equation, lambda of minus 1 by tau plus 1 is what is it, it is 1 minus 1 by lambda of tau, this is 1 minus lambda of tau, okay, this is 1 minus 1 by lambda of tau. Now you see, as we have limit imaginary part of tau tending to plus infinity, okay, lambda of tau by e power I pi tau is equal to 16, okay. And so but you see our tau is x plus I y naught and imaginary part of tau is y naught. So you assume y naught to be sufficiently large. If you assume y naught to be sufficiently large, then you can approximate lambda tau to 16 e pi I tau, okay. So if y naught is sufficiently large, okay, lambda of tau can be approximated to 16 e power I pi tau, okay. And what is this 16 e power I pi tau? 16 e power I pi tau is just 16 into, well, it's e power I pi, my tau is x plus I y naught, okay. So it is e power I pi x plus I y naught, right. So I am going to get 16 by e power, so I will get e power minus pi y naught, so I will get pi y naught in the denominator, alright, and then I will get e power I pi x, okay, this is what I will get, right, and this is with what, this is with x varying from 1 to 0, I need to look at 1 by lambda tau, okay. So let me write out what 1 by lambda tau is. So you see it is a little bit involved in the sense that you have to trace, you have to keep track of all these small arcs and trace their images carefully, okay? And the whole proof is literally doing this in a careful meticulous way, right. So you see now, see, because I want to calculate what is lambda of tau double prime, lambda of tau double prime is will be approximated to, well, what is it, it is 1 minus 1 by lambda of tau, I mean this is equal to this, and that is approximated to 1 minus, well, I will get reciprocal of this, so it is going to be e power pi y naught over 16, okay, into e power minus I pi x, okay, this is what I will get. Now you see, now go back, now look at the lambda plane. You see, if I look at e power pi y naught by 16 into e power minus I pi x and let x vary, x decrease from 1 to 0, then here pi x minus pi x is going to it is going to increase from minus pi to 0. So what I will trace is, I will trace a circle centered at the origin, so this is a circle centered at the origin, a rather large, I will trace a semicircle, so what I will get is I will get this, okay, this is what this will trace without the minus sign, only this, okay. So the angle changes from minus pi to 0, alright, so I will get this, okay. So this is what you will get for e power pi y naught by 16 times e power minus I pi x, this is what you will get, okay. Now if I take minus of that, I will get this circle which is just reflection about the origin, z going to minus z, okay. So what I will get is, I will get, you see, I will get a circle like this, so I will get this circle, this will be minus e power pi y naught by 16 e power minus I pi x, so I will get this semicircle, alright, and you see, mind you, the radius of this circle is pretty large, it is e power pi y naught by 16, and you have assumed y naught is positive and large enough, so this is a huge circle, it is a huge circle. So this is a huge semicircle in the upper half plane, okay, and centered at 0, but then I have to add 1 to it, so it will be slightly displaced, alright. So the net effect is that, you know, if I, so if you assume that y is y naught is pretty large, okay, then this displaced, then shifting this upper semicircle by 1 is going to be negligible. So what you are going to get is, you are going to get something like this, your final image is going to be something like this. So you will get something like this. This is going to be my final image, okay, this is going to be my final image. So you see, this is what this is going to be, alright. So the moral of the story is that if I apply lambda to this small segment, I mean to this small piece of the semicircular arc, alright, I end up getting a full semicircular arc, something that is close to it, because you know there is an approximation here. So I get, of course I get a curve, but what it says is the curve can be approximated by the semicircular arc, alright, and the approximation can be made to any degree of accuracy you want by simply taking y naught large enough, okay. So and mind you therefore you see b double prime, alright, will go to will start here, alright, and then so I will have to be careful about the orientation. So if one keeps track of this, I end up with that is correct. So you see this will, so this point will be lambda of b double prime, okay, and this point will be lambda of c double prime. This is what I will get, and I will get this large semicircular arc, okay, which will approximate the curve that I will get, which is the image of b double prime c double prime under lambda, alright. So I have been able to get hold of the image of this portion of the curve, but I am thinking of this as in the I am thinking of it as actually lying in the tau plane itself when I apply directly lambda to it, alright. But then so I need to see the next thing I would like to do is to see what happens to the image of this portion of the curve c prime to d prime under lambda, okay. I need to find out what is the image of that. So you can guess, you see this portion of the curve is close to 1, lambda at 1 is infinity, so you got a very large semicircle in the upper half plane, whereas this portion of the curve is close to 0, okay, and the lambda value there is 1. So it is natural if you expect a very small semicircle, okay, as the image of this portion of the curve, alright. So let us write that. Next look at the image of c prime d prime under lambda, okay. So look at the image of c prime d prime under lambda. Notice that c prime d prime is in the, if you want to think of it, is in the tau prime plane where tau prime is -1 by tau and tau is varying on CD. So you see, so tau is in CD, okay, is in the line segment CD, tau is of the form x plus I y naught, okay, with x as you go from C to D, x is going from is decreasing from 0 to -1, okay. So -1 less than or equal to, I mean 0 greater than or equal to x greater than or equal to -1, okay. This is the parameterization of CD, okay, for a point tau on CD. Then tau prime of tau is, well, -1 by tau, because tau prime of tau is -1 by tau, and we have seen that this map tau going to -1 by tau takes CD onto c prime d prime, alright. So so you see lambda of tau prime will be lambda of -1 by tau, okay, and again I use the functional formula. Lambda of -1 by tau is 1 minus, I guess 1 minus lambda of tau, it is 1 minus lambda of tau, okay, it is 1 minus lambda of tau, and you see, and again lambda of, but you know lambda of tau can be approximated to 16 e power I pi tau if y naught, which is the imaginary part of tau, is sufficiently large, alright. So so you see, if you calculate so you see lambda of tau prime can be approximated to 1 minus 16 e power I pi tau, okay, and well this is so this turns out to be, if you write it out, this is going to be 1 minus 16 e power I pi tau is x plus I y naught. So this is going to be 1 minus 16 e power I pi x e power minus pi y naught. So I will get 1 minus 16 by e power pi y naught into e power I pi x. This is what I will get. Now you see, trace the image of C prime D prime under lambda, okay. So I have to trace this. What will I get? You see, in the, so if you take the lambda plane, okay, then 16 by e power pi y naught e power I pi x is going to be a circle centered at the origin with a very small radius, because you see y naught is pretty large, so this is a very small radius, and it's centered at the origin, and you see the angle is changing from, you see, 0 to minus pi, okay. So you see what you will get is you will get a small circle here like this, okay. So this is what you will trace if you plot 16 by e power pi y naught times e power I pi x. This is what you trace. Now if I want to trace minus of that, then I will have to take the reflection of that about the origin. So what I will do is, so essentially what I will trace is, so I will get this. So it's not very neat, but so you see I will get this. So this will trace for me minus 16 by e power pi y naught into e power I pi x, okay, and this will be centered at 0, and then if you want to trace the image of this, you will have to shift it, you have to add 1 to it, so you have to shift this whole arc to the point 1. So you know, if you have the point 1 here, alright, then what I will get is I will get this, okay, and this will be the image of this, alright, and what will this point be? This point will be the image of C prime. So this point will be lambda of C prime, okay, and this point will be lambda of D prime, okay, and again of course I will get I will get a smooth arc, but it's approximated by this semicircle, okay, but in this case, so in this case I am getting a small semicircle on the upper half plane centered at 1, alright. Now I think more or less we have come to the end of the story, except that I need to also know, because you see I am trying to plot the image of this contour under lambda, okay. So in fact what I have done is, you see, I have taken the following contour, so let me, so instead of taking this full contour, okay, I'll take this contour and I'll cut it by this piece here, and then continue along this, cut it by that piece there, and then go back and come up, okay. So you see, so let me write that down. Now look at the image of the following contour under lambda, okay. So you see this is my contour now, So let me draw it properly, a bigger diagram will help. So here is my, so this is my tau plane, right, and you see I have this point which is this line, and then I have this large, I have this semicircle centered at half. This is the origin, right, and then I have this line segment, okay, and I'll call this as A, call this as so let me keep these notations properly. A, then I'll take this portion of this segment, okay, this portion of the segment is this portion, so it's B double prime C double prime, okay, but think of it also as lying in the tau plane, alright. So this is B double prime C double prime, okay, and then this is of course B, okay, this is C, okay. So this of course this line segment is imaginary part of tau is equal to y naught, right, and then I have so you know I go along this arc, then I go along this, okay, so I avoid this piece, so I avoid going through one, right. So I come like this, I come up to B double prime, then go along this semicircular the circular arc to C prime, C double prime, then I go to B, then I go to C, then I come down, and then I take this piece of the arc, which is the piece from C prime to D prime, right. So let me draw that. So C prime, here is D prime, okay. So my you see my contour is this, right. So you see this is my contour, I start with C, then go to C prime, D prime, then I go along this, then go to B double prime, C double prime, then go to B, then go to C. So this is my closed contour, and I am trying to look at the image of this. Now let me draw the image. So you see okay, so let's look at what we get. So you see if I started at the point at infinity, I would have got 0, alright. Perhaps the best thing that I should do is maybe start with looking at first the image of C prime D prime. So you see if I take C prime D prime, I have it somewhere here. So the C prime D prime is approximated by a small semicircular region, okay, which is in the upper half plane. It's a small semicircular arc in the upper half plane centered at 1, right. So what I'll get is, so here is, so let me draw, let me put 1 here, okay. So I'll get this, so this will be lambda C prime, this will be lambda D prime, okay. And you see the fact is you see I'm avoiding going to 0, therefore but you know as you go to 0 lambda goes to 1, so I am avoiding 1, alright. So therefore you see what will happen is, if I so what you should realize is that this whole shaded region here, okay, is actually being mapped to this region, which you can understand by making y larger and larger. As you make y larger and larger and larger, you see these circles here, they will shrink, okay. So the fact is that this whole piece here is being mapped to this approximately semicircular region, alright. Then you see from D time then from D prime to B double prime, I have to go along the boundary, and you know along the boundary lambda is of course continuous, and you know it's real, okay. So from lambda of D prime to lambda of B double prime, I will have to go along the real axis, okay. So but what is lambda of B double prime? That is a huge, you see there is a huge semicircle centered approximately, it is centered at 1, alright, but it is a huge semicircle. It starts at lambda B double prime and comes to lambda C double prime, alright. So what will happen is, you see, I will get a well, if I draw it properly, I will end up getting a let me just look at the diagram I have drawn so that I do not draw something that looks too disproportionate. Yeah, that is right. So you see, well, so I will end up getting a rather oops, that was too huge a circle I am trying to draw. Do not mind if it does not look like a semicircle. Okay, let me draw it a little smaller. Okay, so you see I will get something like this. Okay, so this point will be, so this is this diagram, you see it is lambda b double prime and approximately going to lambda c double prime. So you see, so this is lambda b double prime, and it goes on like this, and you see from lambda d prime to lambda b double prime I am still on the real axis. This is the image of this semicircular segment, okay, by continuity, right, and because it is real, right, then I get this huge semicircle that goes all the way, and here I end up with lambda c double prime. Okay, I end up with lambda c double prime. Then you see from c double prime I go all the way up to b, alright. You see if I so of course if I go all the way to the point at infinity, I will again, so then the image will go to 0, alright, but the point I stop somewhere here and I need to find out what is the image of BC, alright, I need to calculate what is the image of BC, and perhaps that is the only thing that I have not calculated, but that can again be done directly using this this estimate. So let me do that also. So you see lambda of so what is lambda of BC for tau in BC, tau is x plus iy naught, and as I am on BC x is decreasing from 1 to 0. So you see 1 greater than or equal to x greater than or equal to 0. Okay, if I calculate lambda of tau, it will be so lambda of tau, because y naught is sufficiently large, lambda of tau can be approximated to 16 e power I pi tau. So it can be approximated to 16 e power I pi tau. Okay, so this will turn out to be 16 e power I pi tau is x plus iy naught. So what I will get is 16 e power 16 by e power pi y naught into e power I pi x. Okay, so the result will be, if I plot this, I will get a circle, a semicircle centered at the origin, alright, it will be centered at the origin, and the x is decreasing from 1 to 0, so pi x is decreasing from pi to 0. Okay, alright, so I am going to get a small semicircle, alright, and it is going to so it's going to be traced like this, okay, and it will be centered at 0. So the image of the segment BC will be a small semicircle here. Okay, so this will be lambda of B, this will be lambda of C, and I will get this semicircle. Okay, and the fact is, I mean the fact that you must understand is, well, of course I did forget to say that, you see, if I take this small region here, what happens to this small region? You see, this small region is a neighborhood of 1, but lambda goes to infinity at 1. Therefore, you see, as I make this, if I make y larger and y naught larger and larger, then this arc will become smaller and smaller. So the image of this arc will become larger and larger. Therefore, this shaded region actually corresponds to the exterior of this circle. This is what this small region is being mapped to, because if I make y0 larger and larger, this arc will shrink, and as this shrinks this guy will become larger and larger. So this shaded region will go to the exterior of this semicircular region, alright. And then also notice that if I take this shaded region, okay, then this shaded region is this is a neighborhood of infinity, and at infinity the lambda dies to 0, alright, lambda dies to 0. Therefore if I make this segment, if I push this segment higher and higher, I am going to get smaller and smaller semicircular arcs centered at the origin. Therefore that this shaded region actually goes to this piece, okay. And therefore as I go from B, see if I go from C double prime to B by continuity, you see I go from here to here, okay. Then from B to C I get this small semicircle, then from C to C prime I get this piece on the real line. So actually this gives you the complete image of lambda. Now comes the final point. You see, give me any value lambda naught in the upper half plane, okay, give me any value lambda naught in the upper half plane, which is then you see I can adjust this y0 to be large enough so that lambda naught lies inside this contour, the image of this contour. What does it mean? It means that the winding number of lambda, okay, you see the winding number of this, the winding number of the image of that contour in the lambda plane about any point in the upper half plane is 1, but the winding number is precisely the number of times that value is taken by the function, okay. Therefore what it tells you, it tells you in one stroke that every value lambda naught in the upper half plane is taken by lambda, and it is taken exactly once, okay, it is taken exactly once. So this proves that lambda is a one-to-one holomorphic mapping from omega to the upper half plane, okay. And of course we have already proved that you can extend it to the boundary in a continuous manner, so that at 0 it takes the value 1 and at 1 it takes the value infinity, okay. So that literally completes the proof of the theorem, right. So in fact this proof also tells you that lambda is actually monotonic on the boundary, okay. So so there is no question of the lambda going somewhere like this and then stopping at some point and then going back and then going forth. Such things do not happen. The monotonicity is because except for the points 0 and 1, at all other points lambda is analytic, okay, and if the derivative vanished, the mapping will not be conformal and you will never be able to get a semicircular neighborhood in the image, okay. So therefore this argument actually proves that lambda takes every value in the upper half plane precisely once, and lambda on the boundary is monotonic, okay. So that proves the theorem. Now you can take you can use the symmetry of the argument and write it out and show that the mirror image of this omega about the imaginary axis will be mapped by lambda onto the lower half plane, right. So that completes the proof of the theorem. So at first it might look a little confusing, but the point is that one has to be patient enough and draw a lot of diagrams and keep track of these estimates, okay. Then you will be then you can understand how lambda actually maps, right. So I will stop here.